In today's video, we'll be talking about the conservation of mechanical energy revisited once again. I know the previous lesson was kind of challenging to wrap your mind around, at least I think it was. So this lesson is going to cover a lot of the same concepts that were covered in lesson 4, but just again, kind of taking a look at it because it's an important underlying theme in physics, this idea that mechanical energy can be conserved depending on the type of forces that are interacting with an object. So after watching this video, you should again further understand how mechanical energy can be conserved, and then keep in mind what is the difference between a conservative and non-conservative force. If you're having a hard time identifying that, these problems become relatively challenging because you don't know if mechanical energy will be conserved or not. So keep that in mind as you go through this video. All right, so let's again do a little bit of review. If conservative forces are the only forces doing work on an object, then there is no change in the total amount of mechanical energy. Now remember, what is a conservative force? Okay, what is a conservative force? Basically, in first semester physics, there's two conservative forces. There is the spring force, and there is the force of weight, or a lot of times you hear me calling it the force of gravity. Those are basically it. When we get into second semester physics, there's an electrical force, but we'll worry about that later. Okay, so for right now, all we're worried about is the spring force and weight. All right. Now, if the conservative forces are, if it's only a spring force or a weight force acting upon an object, then we can actually simplify our equation from the previous lesson, where we have the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. Okay, these two sides of the equation must equal each other out. Now, if you remember the old equation, if a non-conservative force was involved in this, we basically had another term right here as plus work done by the non-conservative force. But we aren't worrying about that right now because we're saying, well, only conservative forces are acting upon an object. Then we can actually just completely cancel that term out because there is no forces coming from non-conservative pieces. So let's take a look at the relationship between potential and kinetic energy. Potential energy is increased due to the stretching or compression of a spring. Okay, so remember the spring force is a conservative force, and basically if you take a spring and you pull it really far apart or you compress it, basically potential energy is going to increase due to that either pulling or compressing. The potential energy of an object is also increased if you increase its height above the Earth. Okay, you're increasing its gravitational potential energy by increasing its height above the Earth. In both of the above situations, the kinetic energy should really, in theory, decrease because as you increase potential energy, the amount of kinetic energy in the system has got to be going down. So if you start to compress a spring, in theory, things should be starting to slow down. Or if you throw a ball into the air, as the ball gets higher and higher and higher, it should begin to slow down. Its kinetic energy should be decreasing. But the total amount of mechanical energy, so if you look at potential and kinetic together, the total amount of mechanical energy present would be conserved, okay, because it's only conservative forces acting upon this object. So let's take a look at a spring, and we'll just kind of do an example with a spring. There's a lot of ways you can look at this, but here is a spring, and I am not a good artist, so I apologize right off the get-go. This spring is just sitting there on the table. It's what we call relaxed, okay? It's in a relaxed state, and it's at rest, okay? At this point, this guy has no potential energy and no kinetic energy, okay? Because that spring will sit there and do nothing for the rest of its life if we allow it to do so, okay? Now, let's say we take that spring and we compress it, okay? So now it's smushed, it's compressed. Basically, it's compressed and it's at rest still, okay? So something is pushing on it, okay? And holding it in this compressed state, and it's at rest. Does it have a lot of potential energy, a lot of kinetic energy, no potential energy, or no kinetic energy, or somewhere in between? Well, the answer is if it's at rest, it has no kinetic energy, and I hope it's okay. I've been abbreviating kinetic energy with KE, kinetic energy. No kinetic energy because it's not moving. Okay, it's at rest. It tells us that right there. And it would have a high potential energy, which I abbreviate with PE, okay, because it's compressed. It has the potential to begin moving. As soon as, if there's two hands holding the spring together, as soon as one of those hands pulls away, the spring is going to uncompress. Now, let's say we begin to release this spring, and if I could like freeze a frame, it's starting to move, okay? There's starting to become some motion, so it's expanding. It's beginning to expand. At this point, what would be the potential energy and the kinetic energy? Would it have any? Would it have a lot? Would they be about equal? Well, at this point, it just began to expand, and this is not using numerical terms. This is very much so kind of a qualitative approach, just kind of saying, high, low, whatever. We would still have a high amount of potential energy because it hasn't really expanded a lot yet, but it would have some kinetic energy or a low amount of kinetic energy. It's beginning to move, but it hasn't really reached its peak, if you will, okay? Now, let's say it gets back to the relaxed state, or the state it was initially in before anyone compressed it, but it's still moving. If you kind of think about a spring, it's going to expand past that relaxed state point, okay? It's going to actually blow through that point and keep going. It's going to continue to stretch out. At this moment, we actually have a very high kinetic energy, okay? It would be moving the fastest it possibly could be, and no potential energy, okay? And the reason why is it's at the point where it was relaxed, okay? So I'll call this relaxed but moving, okay? So it was now it's at the same length as it was when it was relaxed, but now it's moving. It's going to blow through that point. It's going to keep being stretched until it gets to a point where it stops, and that's going to spring back to its relaxed state, okay? So at this point, I have a high kinetic energy and no potential energy. If we were to start attaching numerical values to these examples, when you add up the kinetic and potential energy in every single situation, the total amount of energy, the total amount of joules in each situation would be the same number. Okay, so let's say you have 100 joules here. Well, if you have no kinetic energy, all 100 joules will just be going to potential energy. At this point, where you have high potential energy and like low kinetic energy, and let me just change to a different pen color so things, I guess, stay kind of nice. Maybe you'd have 70 joules of potential and 30 of kinetic, okay? But if you add these two up, it's 100, okay? And at this point, if you have high kinetic energy and no potential energy, well, you'd have 100 joules of kinetic energy and 0 joules of potential. And this is what is meant by mechanical energy is conserved. Basically, if you add up the potential and kinetic energy together, it should be the same number all the way through, okay? As long as there's no non-conservative forces acting upon the object, it would be conserved, okay? Let's take a look at another example. I don't know how many of you guys have ever gone sledding before. If you haven't, try it. It's pretty fun. But here's a sledding hill, okay? And you're at the top of the hill at rest, okay? You're at rest. Okay? And your friend's just about to push you, okay? What a guy or gal, whoever it is. What is your potential and kinetic energy at this point? Well, at this point, your kinetic energy would be 0, right? You aren't moving. So you have 0 kinetic energy, but you have a high amount or a lot of potential energy, right? Because you're at the top of a hill. Now, what is that potential energy going to change into as you get pushed down the hill? It's going to change into kinetic energy, okay? So like if I were to freeze a point, say like in the middle of the hill, let's say like right here, at that point right there, you would again, you would have like maybe like, I don't know, some kinetic energy, and you would have some potential energy. Okay, it'd be kind of maybe equal. Maybe you have equal parts of it. I don't really know because we aren't using numbers. But again, you can kind of see how some of that potential energy from this point here has been converted into kinetic energy, which is allowing the sled to move. Now at the base of the hill, as you're like just flying along here, just having a grand old time, what would your potential and kinetic energy be? Well, you would have no potential energy because you have no height above the earth, but you would have lots of kinetic energy. Okay, so again, another example of, now this time, gravity having mechanical energy being conserved, okay? Now, we haven't really talked about pendulums per se, but a pendulum basically, the only force acting upon a pendulum once you get it swinging is the force of gravity. Okay, so here's a pendulum, and the thing at the end is called a bob. Okay, how nice it's named that. I'm going to draw a dashed line going down the center. This is where the pendulum would hang if it was at rest. Okay, if that was a straight line, that would be great. But right now it's pulled back to this point here, and this would be where it'd be if it was at rest. Okay. Again, I'm going to ask you, well, if this thing is just being held at this point right here, what would the potential and kinetic energy be? Well, it would have a high amount of potential energy, right? And it would have 0 kinetic energy. Okay, but let's freeze frame it like in just a little bit later. Let's say now it's here. Okay, now it's here. It's moved from here to there. The potential energy would still be some. Okay, you'd still have some numerical value of it, and you would have some kinetic energy. Okay, now just because I'm getting really messy here, I'm going to extend this line way down. But let's say the pendulum, which somehow just mysteriously got really long, but let's say it's at this rest point, but it's flying through it. Okay, it's gonna keep on going this way, right? But at this exact moment, when it's right here, what would the potential and kinetic energy be? Well, you would have 0 potential energy and a whole mess of kinetic energy. You'd actually have all the kinetic energy right there. That would be the fastest point of the pendulum, at the bottom part of the swing. Okay, so hopefully maybe this helps a little bit in terms of understanding how mechanical energy can be conserved. Okay, let's do an example problem where we actually deal with some numbers. Okay, it says a falling ball is represented in 2 resistance-free situations. Okay, so there's no friction, basically, is what that's saying. In one situation, the ball falls off the top of the platform to the floor. In the other situation, the ball rolls from the top of the platform along the staircase-like pathway to the floor. Indicate what forces are doing work on the ball, is mechanical energy conserved, and then fill in the blanks for the 2-kilogram ball. Okay, so once this ball gets moving, what is the only force acting upon it? Okay, and so the force acting upon this guy would be gravity. Okay, and gravity is a conservative force, and so is mechanical energy conserved? The answer is yes. Yes, it is. Okay. So let's take a look at right up here. At the very top, it says it has a potential energy of 100 joules and 0 kinetic energy. Okay. Let's take a look at this situation down in the bottom left-hand corner. It wants to know at the very base, right before the ball hits the ground, like the instant before it hits the ground, what is the potential energy, what is the kinetic energy, and what would the velocity be? Well, if the ball is right about at ground level, the potential energy at that point would be 0. Okay, because it's at the ground level. And at this point, the kinetic energy would be very high. How high? Well, the kinetic energy must, and that's supposed to say KE, must equal what the potential energy was. It must be 100 joules, okay, because it had 100 joules, and now that all those 100 joules have been converted into kinetic energy. Then, to figure out the velocity, I can just use the formula 1/2 mass times velocity squared, where the mass, they say, of this ball is 2 kilograms, and the velocity is what we're looking for. So I have 100 joules equals 1/2 times 2 times v squared. And if you do that math problem, and don't forget to take the square root of your answer, you should get a velocity of 10 meters per second. 10 meters per second. That would be the velocity of that ball right before it hits the ground. Okay, let's take a look at this scenario here in this middle part of the hill. Okay, it says the potential energy is 50 joules. So the other 50 joules must have been used as kinetic energy. So this blank right there would be 50 joules. Now I'm going to kind of switch over to this spot right here. If the ball hasn't changed its height at all, would the potential energy have changed? And the answer is no, it wouldn't have. It would still be 50 joules. Okay. Now, what would the kinetic energy be at that point? Well, the kinetic energy must then also be 50 joules because we know this is a friction-free ramp, and so none of it was lost to friction, and so the kinetic energy must have been the other half or the other piece of what we started with. So if we had 100 and 50 of its potential, the other 50 must be kinetic. Now, to figure out the velocity, again, we're going to use this equation where kinetic energy equals 1/2 mv squared. And 1/2 times 2 times the velocity squared, and then the kinetic energy here is 50 joules. If you do that math problem, you get a velocity of, I believe, 7.1 meters per second. Again, that would be the velocity. Now here's kind of a shortcut. This problem is actually done, even though there's another situation right down here on the bottom. What must the potential energy of this ball be if it is at the ground level? It must be 0 because the ball is directly in contact with the ground. What is the kinetic energy? Well, the kinetic energy must be then 100 joules. All of the potential energy has been converted into kinetic energy. So what would the velocity be? Well, we already solved for that, right? That was done right here on this left corner. The velocity must be 10 meters per second. And you can certainly try it if you want to, but it will work out that it's 10 meters per second. So whether the ball falls off the edge of the cliff or if it rolls down a ramp, as long as it's friction-free, in the end, the velocity will be the same. Hopefully this helps kind of clarify the conservation of mechanical energy. That actually is it for this video. I'll see you guys next time.